All right, I just want to welcome everybody to the Planetary Sample Science Seminar. This is our last seminar of the semester, but we will start up again in the fall of this year. I just want to announce a few things. First, I want to thank Ricky Guest, who is our host here, for providing us all his support for the seminar series, and also to Beth Hoff for all her organizational work and lining up speakers, putting together posters, and connecting us here at UNM to the world. Also, I just wanted to also mention that this seminar is hosted by Survey, the Institute of Meteoritics, and the UNM Grand Challenge. Before I introduce the speaker, I just want to have another fairly sad announcement. Is a member of the Institute of Meteoritics, Horton Newsom, passed away last Friday, April 19th, and we are very saddened by the loss. Horton was a great guy, very innovative, and came up with some really terrific ideas during his career and helped an awful lot of individuals just coming into the planetary science discipline. And, he will be missed both at the Institute of Meteoritics, the University of New Mexico, and in planetary science. I'm delighted to be able to introduce a CASA Moon team member who will be giving a talk today, and that's Katarina Miljkovic. And she is from Curtin University, as you can see from her first slide, and the presentation is connecting samples with source craters via impact modeling. Katarina, it's all yours.
Thank you very much, Chip, and thank you for that lovely introduction. And hello, everybody. It's great to be with you all virtually today. And it's a pleasure to be delivering this last presentation of the semester. So I hope you can hear me loud and clear. If anything goes off, somebody will ping me, I hope. So today I'll talk a bit about how we can apply numerical impact modeling in the context of connecting samples that we all love and care for, and we work with samples from the moon for the context of CASA Moon, but we also work with samples from Mars, we work from samples from terrestrial craters, and then by studying samples, how much more we can learn about the source crater by actually looking into shock physics and impact physics as it is. So a bit of an outline. Apologies for a lengthy slide. I don't have many of them that are lengthy, but my background is in numerical impact physics, and I've spent a big part of the past 15 years or so working with the shock physics hydrocode called iCell, and some of the stuff you'll see today is in 2D, from the 2D version of the code. And that's a shock physics code that can be used to simulate cratering processes in various kinds of rocks. And with that, crater morphologies, excavation processes, ejection, as well as dive deeper into profiling the ejecta, profiling the craters, landing distances, fate of ejecta, and so forth, which is actually in this case connected to figuring out what source craters might be connected to samples that we are all working with. And so the interesting thing about the shock physics is that we have these specific pressure and temperature conditions that are unique to impacts compared to other geological processes that we can then simulate with some level of fidelity. So instead of going too deep into what this can be, I chose to actually present you with a few case studies. So I'll talk a little bit about some of the Apollo samples that a team had believed that could have come from Serenitatis and the SPA basin. It's just one of possible scenarios of connecting source craters with samples. It might not be the exactly unambiguous solution. Then a little bit about the Apollo glass beads that were, not Apollo glass beads, but glass beads collected by the Chang'e 5 mission. And I think that's the first case study I'll talk about. If we got time, I might go back and revisit some stories from West Australian craters that we did in the past few years. And I have to emphasize that these case studies are highly collaborative, and I will be able to answer any questions that are related to numerical modeling. But if you ask me anything related to geochemistry or analytics side of things, I probably will have to refer you to my colleagues, which is probably one of the biggest reasons why I really love and enjoy working with CASA Moon and collaborators that work in geochemistry and analytical side of samples, because that's kind of this together we'll be able to paint a bigger picture. And so we know that preaching to the choir, I guess, is that we do all want this story about the absolute chronology and bombardment history of the Earth-Moon system, because we obviously can't do it on the Earth. That confidently we have to look at the Moon. And in shock physics, in impact physics, we are dealing with super high pressures, high temperatures, and phase changes, and mineral phase changes that are unique to impact cratering processes. And then we can use hydrocodes and shock physics codes to simulate that to some level of fidelity. So cratering process, we use, this is a snapshot from the ISL 2D code. You'll see a little bit more of those during the talk, but 2D code is generally cylindrically symmetric. So what we're simulating is kind of a vertical cross-section of half crater. So we have, so we assume that the vertical axis is the one that is the symmetry axis. So if you spin it around the vertical axis, you get a full crater. And in terms of what ISL 2D hydrocode can do, it can simulate crater formation, excavation, crater collapse, final morphology, compaction of pore space, general compaction, compression, fractures and fragmentation, as well as kind of mesoscale effects, what's happening in rocks. It is an open source code, but it's a controlled open source, so you can find it on GitHub if you're interested in using it. It's been around for decades, but it's been actively developed by several teams around the globe. And it has been validated against other codes and experiments. In a way, it has been benchmarked, so we know what we're seeing is right. So that's kind of a really, really quick intro to the hydrocode and capabilities. And so the first example I would like to show you is a simple crater, let's say 10-kilometer crater on the Moon that would create 10-kilometer crater on the Moon would be a simple crater. If we go bigger than, let's say, 20 kilometer, for sure, we're starting to form complex craters. But nonetheless, if we're looking at even such a small, well, it's not even a small scale structure, it is like a decent structure, we still have to think about what kind of crustal properties we're simulating. And thanks to Grail and other analysis, we have some kind of a estimate of how the porosity changes with depth in a crust of the Moon. And we know that roughly it's decreasing exponentially up to a certain depth, and some estimates suggest about 8 kilometers of megaregolith on the Moon. And we can include that in shock physics simulations to try and get a better estimate of pressures and temperatures being put into the crust and in the ejecta. So here is an example of a 10-kilometer crater. Let's see if I can possibly run this. I understand it might not stream very well, so I'll just run this really quickly, kind of to this point. That's an example simulation of a crater that's 10 kilometers in diameter as a final crater that's opening up into a transient crater. But what we can do with a crater of this size, for example, or any other crater, we can look into ejecta as it's developing. So what you're seeing here in this middle plot here is a very early ejecta, and if we capture it in the early stages of formation, then what we can profile is that how fast does it move, and what were the pressures and temperatures that experiencing in the early ejecta. We can do that for the late ejecta as well, but what we're seeing is that the early ejecta is subject to higher pressures. It's moving faster, or the fastest, and that therefore it has the furthest deposition distance, so furthest landing distance, unless it's escaping lunar gravity. So it needs to move faster than 2 kilometers a second to be capable of leaving Venus gravity, so not that fast. If we're going, then we can let the simulation run a bit longer, and then we can start capturing kind of later ejecta. Later ejecta is, later ejecta is moving slower. There is more volume to it. It's landing proximal to the crater, so it's landing in this kind of 1 radius or 2 radius away from the crater rim. But that big ejecta blanket will move slower, land closer to the impact point, will have less shock amount in it, and obviously move at less ejection speed. So if you're looking at something that is structurally quite changed and challenged, then possibly you're looking at something that's been ejected out of with the earlier ejector, had a higher shock, and therefore it's moving away further from the crater than maybe we might have considered. So with that in mind, I will whiz through the first case study about lunar glass beads collected by the Chang'e 5 mission, and I really wanted to list out all the authors on the paper that was published a couple of years ago now in Science Advances, just to see that there has been quite a team working on the same problem. About over 200 glass beads that are micron size were selected from the regularly brought back by Chang'e 5. And the big effort was to analyze the glass beads. And for the glass beads formation, what was interesting and important to me as a modeler is to try and understand, to get this input about what will be the temperature of formation for the glass beads. And I was told that that would be between 1100 and 2000 Kelvin. Apologies, I work in Kelvin, but you see that in Celsius as well. And that's the analytical estimate based on the compositional samples that were collected. You see it on the right hand side, a snapshot that was of few beads that were probably best looking that were included in the paper. So in terms of theory, we know that spherules can form in a couple of different ways, and the one that was more appropriate here is that it's forming out of melt droplets from the ejector curtain, and the size of those melt droplets is related to the size of the impact and the speed of the ejector. And so plugging all of those estimates into the equation, then we get that for craters that are sub-kilometer in diameter, we have projectiles that are of meter size, of tens of meters of size, with an average speed of, let's say, 20 kilometers a second, which is an average or most likely encounter speed at the moon. Then we find that the largest fragments, according to this estimated theoretical equation, would be of micron size, which kind of is an extra confirmation that we're looking at that we're looking in the right crater size range for source craters. So that was the first check. What we did then is I should have said that as well. So this is where the samples were collected from. So if you see CE5 is the position of the Chang'e 5 sample that believed to have possibly sampled the proximal ejecta from 2 craters, one from that's about 100 meters in size and the other about 400 kilometers in size. And we would have imagined that the landing site and the collection site would have sampled the proximal ejecta from these 2 craters. Okay, so the next thing is that, okay, so confirming that the melt droplets that relative to their size, that they should have come from a crater that is sub-kilometer. The first source crater, we thought, oh, what about these 2 craters that are in the immediate distance? So when we started looking more into numerical modeling side, then I've created a range of impact conditions for craters that are between 200 meters and 1200 meters in diameter, in final diameter. And so what you're seeing here is probably the smallest kind, where we made an impact into homogeneous target, which is on the right-hand side, like homogeneous basalt, and an impact into homogeneous basalt, but it's got about 8 meters of quite fluffy regolith, like loose terms fluffy regolith, which is what we believe from that landing area. That's how much regolith was there. And what you see in this kind of olive color is the ejector material that is subject to the pressure, to the temperature change that is appropriate for the conditions for temperature, conditions of temperature that beads can form in. And so there is a range of impact conditions that I made in the short physics code and in ICEL. So that was the smallest. This was the actually, sorry, no, these were not the smallest one. This is slightly bigger. This is probably a mid case. The smallest case was this one, only 4.5 meter projectile. That you can see here, there's 8 meters of regolith overlaying a bedrock, and versus a case where there's just homogeneous bedrock here on the right hand side. And the problem here is that the way the ejecta is formed, it is fine. The temperature conditions are met in both cases, but what is different here is the pathway of the ejecta progression of this material being ejected out of the crater, because it's being diverted a little bit by having kind of different layered structure at the impact site. That will certainly affect our estimates of landing distance. That's why this is important. Here is an example of a time series. So an impact that happens in the far left side, and then as basically this is contact and compression stage of the impactor bearing inside the target, and as it's bearing in, it's starting to create this early ejecta, and that more and more ejecta gets out of the crater, but only a find this initial interface between the kind of during early cratering is meeting the temperature conditions, and that only a sliver of the ejecta being thrown out of the crater in terms of volume is actually meeting those bead forming temperature conditions that is thrown out of the crater. So, and that is particularly interesting for these small craters, because the rest of the ejecta curtain here is actually at low temperature, so it won't meet the temperature conditions for forming glass beads throughout the entire ejecta blanket, just a sliver in volume. So when we look at the landing distances in all cases, as you can see, craters that vary from 100 meters in diameter to 1,300 meters in diameter. The most probable landing distance for ejecta for the volume of the ejecta that is meeting the temperature conditions for forming glass beads is landing at around 25 kilometers. That's like most probable landing distance. But these are the so-called KDE. So these are the data density distribution, saying these are the most likely landing distances, because we have ejecta going everywhere. So for the smallest craters at 100 and 210 meters, there we have kind of these funky looking landing distances, and they're only because we've made craters into 8 meters of regolith overlaying bedrock. And for the other craters that are bigger than 0.5 kilometer, then that fine layer of 8 meters regolith no longer really took an important role, because that layer became too thin to influence the ejecta mobility. So in any case, we're looking at and most likely a landing distance between 25 and maybe 50 to 70 kilometers distance, which in a way discounts the 2 little craters that are in the immediate vicinity of the Chang'e 5 landing sites. So made things a little bit more interesting, a little bit more complicated. And if you're wondering why we all have the same landing distance basically for all different crater sizes, and that's because we have the same impact energy, same impact speed, and we are inputting, and the energy change is scaling very well with impact speed. So we're looking at creating this ejecta sliver at a particular temperature range that is moving at a particular speed. So it's landing roughly in a similar distance. This is not volumetrically studied, it's just looking at for which crater, how far would it go. And I've shown that one. So if we were to try and see which crater is more likely to be a source of a crater, the bigger the crater, the more the ejecta. So the bigger craters would have a higher chances of being a source crater. But this is what you see here is the region of the Mare Posalt where Chang'e 5 landed, and you can see the geological unit here outlined. This is the young lava flow, young, about 2 and something billion years old, one of the youngest lava flows that is on the moon. And there are no big craters in this region. They're all smaller than about 6 kilometers. So we've only looked at the statistics up to about that size. So the bigger the crater, the more likely it is, but not the one that's very, very proximal. Okay, so I'm going to switch gears now, and I do acknowledge this speaking to myself in an empty room. I can't really follow the audience, and if you've got any questions or any confusions, so I'll kind of keep going, and hopefully we'll have some time for questions. So I would like to move on now to the studies that we did with the Apollo samples, and because Apollo samples are quite old and more likely have come from an impact basin on the moon. So we're going to switch gears and now talk about very big craters, because I'm moving on to the next case study. So impact basins are quite unique geological structures, because when they formed within the first 700 million years or so following moon formation, they were so massive that they've certainly ejected quite a lot of material. They caused crustal overturn, and they've also pulled mantle closer to the surface, and they have rejigged the entire crustal structure in that region, including causing quite a lot of melting. But here we'll mostly talk about the ejection process, just to kind of bring you up to speed. Compared to the little craters, if you have, I'm going to try and run this. Is one of the little examples. So what you see here is basically basin forming, and what you see on the scale here is shear pressure. And not shear pressure, it's the absolute pressure, shear in terms of massive. And that means that it goes far above the temperature melting, and it causes even superheating and all that stuff in terms of how it does affect the crustal and upper mantle structure. So if we were to stop that and just look at some snapshots, so in the early ejecta, kind of basically just before the crust overturns and start collapsing into the basin, we can pause the simulation and look at what might be the breakdown of alteration in that ejecta curtain. And we see that majority of the ejecta here is an odd thing is that I don't have the orange color. I don't know exactly. No, I would probably say it would have been I don't know. I don't know what the temperature is. So what you're seeing on your left, basically stratigraphy on the right hand side and the peak pressures on the left hand side. So we're seeing quite significant peak pressures in the very melt pool, going over 30 GPa. And if we were to look at what's happening to the ejecta, then we have pressures that go up to maybe even 50 GPa, but not in the full volume of it. It goes above 10 GPa, but then the orange one is the one that I don't have colored here in the color bar on the right hand side, so I can't really explain. It could have been a few GPa order magnitude, but not too much. So it's going to remain a mystery, I guess. But nonetheless, it's just showing you the order magnitude, the pressures that are experienced within a basin during basin formation. Okay, so the first case study will be around the appetites analyzed in a sample from a Apollo 17 collection site, paper led by Anna Chernok 3 years ago, when she wanted to find a source creator for this particular sample. But it was interesting, this sample is particularly interesting because it's got two temperatures, two ages that are measuring impact events at about 4.2 billion years ago, and then again at about 500 million years ago. So that means that in order for this sample to be placed in a Apollo 17 collection site, that it has suffered a couple of impacts, one very early on and another one again that had a moderate heating to it. So a big crater and a small crater. So how would that story go is that it has been excavated by Serenitatis, for example, because originally had this first resting place was at the edge of Serenitatis, being excavated from deep-seated material during basin formation, and then it was moved by an impact into the edge of Serenitatis by the formation of Dawes crater, and then thrown about 140 kilometers away to the final resting place at the Apollo sample site. So in order, that story made sense from all the analytical aspects, all the shock physics aspects, and the history of understanding and analyzing samples using various techniques. But the last piece of this puzzle was then also to try and check whether impact mechanics also makes sense. So this is where I came into play. So what you see here on the left-hand side is one simulation, on the right-hand side is another simulation, just showing you different things. So the top is stratigraphy, the middle panels are peak pressures, and the bottom panels are temperatures. And this is a simulation for somewhere between 4 and 4.5, well, 4.4 billion years ago. One is for one age, the other column is for the other age, just assuming different temperature gradients at that time on the moon. And what we see, the base information itself is relevant, but what we're creating here is a Serenitatis size basin that has some sense in terms of when we compare with gravitational signatures, we kind of get something that's of a Serenitatis size. But temperature gradients were also important at the time of base information, and we know those from thermal evolution models that have been published in the past 10 years, because that gives us the kind of initial condition for temperature at depth before we shock it with a big impact. The point is, what we're trying to look at are basically the edge of Serenitatis. So somewhere around 300 to 340 kilometers away from the impact point. So kind of like here, I don't know if you see my cursor. So basically that's the region that we would zoom in and then look at what is the breakdown of peak pressures, peak temperatures, and whether that makes sense with respect to what has been seen in the sample. And the brief answer is yes. So we can say tick, okay, so it is possible that we're getting this sample from this particular depth. It could have come from the upper mantle, and it has been shocked to these particular pressures as observed in the sample. And it was placed in the kind of rim region of Serenitatis. So the next thing was to look at Dawes. So is the Dawes crater that is at the edge of Serenitatis could have actually launched that sample away. And so Dawes is not very big. It's around 15 kilometers across, but it has mare deposits on top of it. So what we wanted to make sure is that we can form the crater. The sample that is being thrown out from Dawes had to have come from beneath the mare basalts and had to have been not shocked to temperatures higher than what was observed in the samples, which meant it could have come from this later ejecta that has less shock in it or a less alteration in it. And so the numerical model suggested that was possible. And then it could have actually then, in that case, landed at about 140 kilometer distance from these particular depths for this particular impact scenario. So we didn't have to try very hard. It kind of this average conditions for impact, size, and speed kind of worked. You probably think, okay, you throw out a chunk of rock, it's fine, it's compliant, but you know, when it lands, what happens to it? And then I guess that's just one thing that to clear up is that if something is flying at sub escape velocity on the moon, so we've got a chunk of rock that's thrown out at a speed that's less than 2 kilometers per second, then chances are the big part of that thrown out rock would survive as it is unshocked. So what you see here is kind of, it is shown in meters because we've chosen a 50-meter chunk of rock to test, but basically it can be dimensionless in some sense. So no matter how big the rock is, the same distribution of shock would exist. There is some alteration in that size of the rock that first meets the land, but then as it compresses into the land and lands, the big bulk of that fragment would actually remain unaltered. And that means that we don't have to really worry about this secondary transfer of rocks around the moon. Okay, so that was a very, very brief overview of connecting source craters with samples in the case of Serenitatis. Whether or not Serenitatis is really 4.2 billion years old based on this sample or not, whether this sample really comes from Serenitatis or not is can still be a question mark, but we found kind of the path of least resistance, and it makes sense. But whether it's an ambiguous solution, probably not, but it is a solution. One more study I would like to show for the moon, for the Apollo samples, comes from one of the troctolites, and that the work that I've done with Ian Garrick Bethel a few years back, where we tried to see if this particular sample that's also collected from Apollo 17 site has been thrown out from the SPA, from South Lake Basin. The interesting part about this to me as a modeler was that it was estimated that the depth from which the sample has been thrown out from is between 45 and 65 kilometer depth, which means mantle, quite deep mantle, but not at very high temperatures, like not melt. And the compositional is consistent being far away from the near side of the moon. And again, I'm parroting back some of the stuff that was given to me as physical parameters to work with the sample. And again, the ejection speeds, the ejection process would have caused basically no shock to it. So a bit of a spoiler alert, this story took a little bit more explaining, and it might not be the best unique solution, but it is one of possible theoretical explanations. So we yes, so in order to say that the SPA might have been the source of such a deep sample being shocked at so low pressures, we kind of ran through a whole series of different base information models just to show that for craters that are of Serenitatis size, even Imbrium size, we actually, when we eject samples from such a deep depths, they tend to be more shocked than we need. So this is just a snapshot series of formation of a coal-dish basin. It's a theoretical example of something that was of 60 kilometer size hitting the moon that would have originally formed something of the size of Orientale maybe. But that's beside the point. What was the point is that if we're throwing out materials from 45 to 65 kilometer depths, then the breakdown of pressures that the material has been subjected to is higher than 24 GPa. So far from 6 GPa that we needed. A little counterintuitive, but it is. It's because it's part of this kind of early ejection process. Same goes for if we looked at different things. We looked at geometrical effects, and if we have a big impact happening on like model simulated on a flat surface versus curved surface, we've concluded that same pressure profile applies. It's just a slightly different distribution because the ejector is moving slightly differently because of the curvature. But again, we couldn't get to this 6 GPa requirement. We've also tried different impact speeds. We worked with as low as 10 kilometers per second impact speed on the moon to 30 for the same kind of mid-size crater of, let's say, Serenitatis Basin or Crisium size basin. They're all kind of similar. We couldn't go lower than about 10-ish GPa to produce to excavate samples from upper mantle. So the reason this is different to the previous one is the previous one was had a different impactor size. So this is slightly bigger projectile size for 3 different impact speeds. Again, we are creating something that is of Serenitatis size or Imbrium size and still can get to low shock pressures from upper mantle depths. So kind of a method of elimination, I guess, is what's been happening here. We've also looked at sensitivity to some of the analytical constraints. And again, if we really, really push it, then in terms of like looking into higher resolutions and all that models, nothing really changes. But when we looked at the whole breakdown of different peak pressures that are experienced in a, let's say, Serenitatis size basin, then the 6 GPa shock pressures, they start at shallower depths at about 28 kilometers and possibly down to 60-ish kilometers depth, but only by a small volumetric fraction of the ejecta. So it's possible if you really, really stretch it, but unlikely. And so that's how we ended up with the SPA, and then this is a simulation of one of many simulations of possible SPA solutions of a 200 kilometers. So now we're going up in size in projectiles. Impact speed here is 10 kilometers per second. We've also done it for faster impactors, but there is also arguments at the time when we were writing this paper that the very early collisions on the moon might have happened at lower speeds than what we see today, and so forth. So this was our favorite case, and in this case, what we're achieving is that for a material ejected from required depths, that we get a reasonable, small but reasonable amount of volumetric part of the ejector that is thrown out from the SPA at 6 GPa or less. And so that was the yay moment, I guess. And then what's the next question is like, so where does this low shock ejector from deep depths land? Well, unfortunately, it lands at the rim of the SPA. So it lands really basically just surrounding the crater, because if something's thrown out from such deep depths, it's not shocked, it's going to be late ejected, it's going to move slow, and it's going to just be basically at the rim. And then the question is like, okay, well, that's great. We've thrown stuff out from SPA from deep depths, but we do need to get that particular sample all the way to the Apollo 17 collection site. So what happened to it? So that's where I guess a bit of squinting is required. So it could be secondary cratering that has moved stuff across the surface. There's plenty more small crater events that happen since SPA formation. So any one of them could have kind of basically thrown it out in one or multiple ejection processes. And as I've shown you in a few slides before, is that we don't really provide, we don't really enable high shock in this kind of secondary movement processes. Like I keep thinking about, I guess, tossing a football around the field kind of thing. Anyway, so and the last question would have been, okay, we've really tried hard to throw stuff out of SPA, which was possible to kind of keep preserving it and tossing it around the globe. But what about if this sample actually could have come from one of the nearby basins that are kind of sufficiently big? It can be any one of the pre-nectarian basins that are barely visible on the surface, but something that's on the near side, something that is really already there. And if you've excavated such a sample at the rim of a basin, then it's very, very proximal to the Pole 17 collection site. And then obviously my question is, you know, it's Occam's razor, so why would we go all the way to SPA if we have at least a few good candidates nearby that wouldn't require this toss the ball around across the whole globe? And I don't really have the answer to that question. The only reasoning is that we simply, if it's a near vertical impact, then we can't excavate such deep depths and preserve the chemistry and cause loss shock. But what we haven't done is assuming more oblique impact processes, more highly oblique impact processes that would have a slightly different distribution of that shock physics around it. And that still remains an open question. We haven't done that yet, so it's an open thing that we can discuss, but something that we probably will look and revisit in the future. So I have whizzed through some of the slides, and apologies if some of this is unclear, and please raise your hand or send me a message later if any one of this is interesting but confusing. To wrap up quickly is one of the things that we're really striving to do, at least my team and I, is to provide more insights over how shocked is the moon overall. So some of the things we can do through numerical impact modeling is that we can really dive deeper into cratering mechanics, look at size of the crater, depth of excavation, ejector deposition with distance, what happens to ejector once it's in flight, shock deformation levels, shock physics, changes in the microstructure. But in order to do all that, we need to consider the state of the upper crust, if it's a small crater, or the general moon structure, if it's a big impact crater at the time of formation, whether that's the thermal state of the crustal structure, or at the time, let's say, these big impact craters are formed. So that is something that, because there's so many decades of moons research that's done in the past, that we have some good constraints over what might be the most appropriate physical parameters, so that we can plug it all in the models and then start providing more of the high fidelity specific details around connecting sources with craters, sources with samples. The ultimate goal, I guess, is providing this absolute chronology for lunar surface ages, and with that provide information about the Earth-Moon system bombardment as well, which you all know, and I'm preaching to the choir here. But doing 2D simulations for me means that we can really, at this point in time, have enough computational capacity that we can do really high resolution impact simulations. And that is required, this high resolution is required if we want to do quite precise and accurate estimates of melt volumes, of peak pressures, or looking at fine elements in the ejection process. Together with my student, Ola Shishputowska, who's part of the CASA team as well, we're trying to provide a roadmap or kind of a lookup table, call it whatever you like. We'll see how it goes. Probably this is something we'll do over the next couple of years, is to really be able to provide some of the key shock features from numerical modeling in terms of what's happening to the crater and what's happening in the ejector for particular sized craters, so that we can assist the community doing all the analytical understanding of samples, so where they might be wanting to look up in terms of specific craters on the moon when trying to connect it with samples. And as always, I'm very happy to collaborate. And as I said at the beginning, this is a highly collaborative project. So I might not have answers to all of your questions, and probably some of you might have disagreed with me with some of the stuff I said in these case studies. But that's what we're here for, I guess, for a good scientific discussion. And I'll leave you with this slide. It would be great to see the community in Perth next year. We are hosting the annual meeting of the Meteorological Society in Perth in July next year. And if we can, we'll do a special session on CASA Moon, but that really depends on the community if you are willing and wanting to come to Perth. So thank you very much. I'll stop here and I'll answer any questions.
That's all.
Katarina, that was terrific. Thank you so much. Are there questions for Katarina? Please don't wait for me to call on you. Just go ahead and ask away.
Question.
Yep, go ahead, Steve.
Hi, Katarina, Steve Simon here. I thought at the LPSC, Jim Head said the South Pole Aiken Basin impact event was an oblique impact. It seems like you're modeling it as a vertical impact. In other
Correct.
words, 76535 contradicts the oblique impact theory.
Correct. It's absolutely correct. We don't know. We simply don't know what was the impact angle for SPA formation, but chances are that it was oblique because that's the play on probabilities. And given its shape, the chances are that the impact angle was not 90 degrees, that it was something that's grazing or something that is moderately oblique. That would have caused a slightly different ejection profile, but nonetheless, we would still have a similar shock profile, simply put, within the crater formation itself. And we might have a little bit more ejecta going one way than the other, and slightly more shock going downrange than uprange. But overall, we will be in the same ballpark as it was a head-on collision. It's just the distribution might have been slightly asymmetric. It's hard for me to hand wave this, especially online. But this example of a head-on collision for troctolite as a source crater. We could have had a moderately oblique SPA and still excavate troctolites somewhere in the rim area of the crater. I hope that slightly answers the question. So Jim is not wrong. And a big part of the community doing SPA modeling and SPA understanding have also suggested a moderately oblique to highly oblique impact angle.
Other questions online? While we're waiting, Katarina, I do have another question for you. This is Chip. Some work that Lars Borg has done and I've worked on with him on 76535 suggests that the temperature at which of its origin, probably at the crust mantle boundary somewhere in that sort of depth, was a little bit warmer than what you were essentially modeling. Probably maybe 100 degrees, maybe a little bit more than that. Would that affect your model at all, or does that original temperature prior to excavation have very little impact on your model?
The temperature profile prior to the impact would or can make a difference because what we're doing by delivering the impact into the crust and upper mantle, we are obviously putting in energy to the system. So that energy will produce some delta T, some change in internal energy, some elevation in temperature. So if we have a hot crust, by adding more temperature, we're getting to the hotter crust. If we have a cool crust, then we're getting to a higher temperature of moderately warm crust. You see what I mean? So the temperature that we are elevating this region by will be fixed. So if we, in layman terms, if we fix, so we're adding temperature regardless of what the background temperature was. So if we are elevating from, so if we're reaching a particular temperature that's quite high, they could have also come from pre-existing temperature gradient plus the energy that we have, internal energy change that we caused by the impact. So I would say that yes, it would be particularly for base information, if the samples are quite sensitive to small temperature changes. For us modelers, that might be not a small temperature change, but for people really working with fine temperature changes in samples might be a big deal. Then yes, we're definitely sensitive to temperature gradients that were assumed at the time of SPA formation, any of the base information. But unfortunately, while we do have a good grip on what might be the most likely thermal evolution of the moon, we still argue what would be the most appropriate temperature gradients at the time of each of the base information. So for us, there might be, between 40 Kelvin per kilometer and 20 Kelvin per kilometer. For us, that's a major difference in modeling outcomes. But for you, you might say, well, anything between 33 and 34 will make a big difference at 60 kilometer depth. And that's something that our models are not super sensitive to, unfortunately.
Okay. Other questions from out there? Nope, I don't think we have anything else right now.
Okay,
Well,
I'm looking online, but I'm not sure there are any, there were no.
Yeah, I don't see anybody with their hands raised at all. And I went to chat and I didn't see anybody have a question in chat. Okay, so why don't we go ahead and if there are no other questions, let's go ahead and end the session. And Katarina, we have some other questions. Go ahead, Kim Cohn. Oh, waving goodbye, I'm sorry. Okay, so while we go ahead and end the presentation, and again, Katarina, thank you so much, and I really appreciate all of what you bring to the CASA Moon team, and hopefully with additional isotopic measurements and textural measurements that we make on some of these Highlands materials, you can play a vital role in our interpretation.
Thank you, Chip. I really do hope so. As much as we can do from the modeling side, we're happy to try and contribute.
Okay,
thank you.
wonderful.
Thank you, everybody, for listening.
And safe travels.
Thank you.
Yep. Bye-bye, everyone, and we'll see you next semester. Thank you all for attending this semester's series of presentations. Bye-bye.